That gets you some right there.
Blue healer coat, Australian shepherd
so
face,
yeah, all of those
German
phosphorates,
shepherd
that's
size, and
nucleophilic
then
acid
husky
substitution with a phosphate.
and shed like
Okay.
Um,
Like, I know that LCK is a kinase, so like whenever A is obviously when we're dealing with an enzyme, but
and so this kinase is magnesium
Oh, you
dependent.
get your
You'll find that
massage
LCK
on.
requires magnesium or manganese, and that's because it has to stabilize that oxygen.
There's that leg.
oh, neat.
It's, yeah, it's a substitution.
Just
Yeah, and
stretches
she
it out.
teaches
He
some
loves
microbial
it.
physiology class, and I was gonna ask you about that one, like in the introduction.
Yeah.
So like his little floppy do.
Little Duclaws.
Little floppy do.
Yeah, no. These
They have
ones,
their- yeah,
these are stuck
huge
in
arms
just like
raised.
this.
Yeah, that's pretty cool.
Because I'm really fascinated about that.
That's so much.
Oh, okay.
Five.
You'll love it. That'll
He's just so chill too.
Because she goes, we have to go through some of this.
Hey, Mike.
And I mean, she broke this down in way more detail and said to add
Yeah,
things to
but
it. So there's things here. I was just like, I don't really know. Like, I'm the type of person that when I see this stuff, I want to know what that means now biochemically too. But I might, she was like, don't overwhelm yourself.
I was just gonna say, put the videos up.
Focus on just these
No.
steps first. And then
put the
there's
videos
a
up.
lot of
But I
it.
will look.
Just from
Thank
what
you.
we went over at the beginning of the semester, we already know what it stands
Yeah,
for.
but
This is gonna be a lot.
Alright.
yeah,
Well, this will be helpful.
this will be good. Yeah. Hi, Dr. Reagan. I warned them you'd be here. You don't have to hide. I also did a plug for your class. So. Straight from the horse's mouth.
Well, you didn't say I wanted to, but
Oh, buddy.
You okay?
let me do it. Because I wanted to drop the class to take it instead of interview. Yeah, I want to take that. I was like, let me drop that.
I was like, why am I doing
It's
this?
too bad. Let me take that instead.
There you go.
He's like, I thought I got this.
You know, so much
more
the only reason I didn't
that than I will the lab.
was I took Adam lunch during the summer with a visiting professor. He was from England. They're different.
God, it is so
I was not required to memorize this. So I would never ask, like, what would be the appropriate reagent to use in this reaction? Because in real life,
You see how red I walked in?
even professional chemists, look that up. You're never trusting that it's all in here. You're always confused by what you know. And so he's just like, this brain power memorizing this. Instead, learn the principles. And I feel like too often in the American system, not just universities, but America as a whole, we focus on memorization. Arbitrary.
I'm coming.
Yeah.
Trying to get there.
Yeah.
I don't know how that
Because I thought I just got a Hi, little buddy.
Hello, my baby. Hello, my darling.
Oh yeah, buddy. Hey, come on, over here. What are you doing? Come lay down.
Plastic is becoming
Nope, lay down right here. Come on, come on.
Yeah.
Come lay down.
Yeah.
I know.
Probably so hot in here. I'm probably gonna ask you the silliest question ever. But how do you train him? Because I just adopted a husky and he's crazy.
Dude. Ah, gosh. How do you explain it in just a sentence? Keep him in your view. Keep him in like his eye. Like, get in his view. Yeah. If you get in his view and not let him get distracted, that's the best way he's gonna learn. I think it's like you gotta get in front of him. Don't let him, look around and because he's not gonna listen to you as soon as he's distracted by something else. But you can get in front of him and like start saying "eyes on me," and like do like a small command.
All right, are we all
Snap
back?
your
Am I missing
snap your
anybody?
finger, and then he's at attention now.
I'll definitely
But
try
yeah,
that.
it's just getting him in your
You moved.
field of view.
You moved.
Oh yeah, absolutely.
Yeah. Well, my husky's
All
big,
right,
though,
we're gonna do this
Well, Huskies
stuff.
are awesome though. So vocal.
So, to summarize where we left off, nucleophilic acyl substitutions, these group transfers, super common. They should be our first go-to mechanism. And they depend on a nucleophile attacking our carbonyl, forming this oxyanion state, and then kicking off a leaving group. And then we talked about oh crud, what if there isn't a leaving group? And if there isn't a leaving group, what do we do?
We just add.
Make it an addition. Protonate it. Right? Good stuff. Let me take it one step further. What if we try to do a reaction? And by try, I mean we identify an enzyme that does this. We know for a fact that this happens. And we want to know how, and we want to know why. What if we find out that, and I'll do it in the simplest possible depiction here. What if we find out that we have a carbonyl that reacts with another carbonyl, and we can tell from spectroscopic data or the shape of the enzyme cavity or whatever that we go through an oxyanion intermediate. So we expect/predict the same kind of mechanism, right? We're going to have an attack of our electrophilic carbon. This is a problem, right? Because I see an electrophile, and I see an electrophile. I don't really see a nucleophile. So here's how we're going to resolve this. Because this happens. Biologically, we need to have this happen sometimes, where we have two electrophiles react. Now kiss, right? What we need to do is turn one of them into a nucleophile. And a hint for us of how these reactions occur is that they require a strong base. They require a strong base to get going. I'm about to show a mechanism that is going to make organic chemists kind of squirm a little bit. You ready for it? No, why? We are going to have our base pull off a proton. Yeah. See, it's not so bad. We're going to have our base pull off a proton here, which would lead to a carbanion, right? We following so far? So I pulled off my base. Wow, I did it. I'm left with a carbanion. And those are not stable. Those are not good. Normally, there's no way I'd be able to do this. If we want to invoke the pKa argument, the pKa to try to pull off a proton is like higher than 20, like 40. Not going to happen. Sucks. But we're lucky because we're doing it adjacent to a carbonyl. And, I don't like that color. So we could think of this as a resonance structure. What's another way we could distribute these electrons? We could form a double bond and kick it to the oxygen. That makes sense? That is to say, these electrons we could imagine swinging in to form a double bond, and to resolve, carbon with 5 bonds alert, these could swing up. And we know that's okay because we know oxygen is good at handling excess electron density. It can chill. This is stable. This is fine. Yeah?
So, a lot of times bases act as a nucleophile, sometimes do. So
Yeah.
why wouldn't it just attack the carbonyl carbon?
That's an awesome question. Thanks, Marlia. Thank you. This relies on the design of the enzyme. If we look at the active site, we make sure, I should have drawn it better, that the base is right there to pull off the hydrogen, to pull off the proton, and nowhere near the carbonyl in space. So we actually use the binding site architecture to favor one type of reaction over another.
You say that enzymes are very specific,
Mhm.
and so would you say they're specific on pKas and that?
Yeah.
Okay.
Oh yeah. This would only work for the substrates it's designed for. Yeah. I like it, Nathaniel. So we have this as an option only because there's some kind of resonance structure we can imagine, right? Some kind of whatever. And that opens up this whole new world. Because now, even though in reality this is probably some kind of resonance, and the true answer is somewhere in between, I can pretend like I have a carbanion. And we know a carbanion is a really good nucleophile. Suddenly I have that rare, that unicorn in the room, right? I have my nucleophile. So where would it attack? At my carbonyl. So it goes in and attacks. So once again, we get to play the game, draw that intermediate. Dun, 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 dun. So talk to your neighbor, see if you can figure out how you would draw the intermediate of that reaction, assuming we already got this carbanion state and we're doing our attack. What is that intermediate going to look like?
The negative on the oxygen or the carbon? Which resonance structure?
We're going to assume we have the carbanion state.
Why did we draw it?
What?
It's resonance.
Because it's resonant. No, hold on. That's really good. Before we start, this was a great question. Why did we even bother going down this rabbit hole if we're not going to use it?
Is it to like make it more possible for the hydrogen to pop off?
Yes,
That's, okay.
you got it exactly. If anyone didn't hear that, the idea is normally this first step of pulling the hydrogen off just wouldn't work. It's only because of this available resonance outcome that you can even imagine this. So let's try it. Draw that intermediate. We're doing it.
Such a hot sweet.
Oh, yeah. I'll figure something else out.
Yeah, I can see it. What? I did, but I had to twice to get
What's normal? That's great. Don't worry about it.
That's his reaction.
Wait, what? Who? You people. All right. Do we think we got it? All right. Anyone feel brave enough to come up and draw it? Wow, that was short. Okay. I'll draw this one. You're drawing the next one. I'm going to have these carbons still, I'm pretty sure. I don't think I deleted any carbons magically. What's the oxygen going to look like? Negative kind of oxygen guy. And I have some new bond, new bond, which came from this guy.
Then you have a hydrogen off it.
I got my little guy.
They're laughing at me.
They're laughing at you.
The same thing they're laughing
Respect
at me.
Nima. He knows what he's talking. Well,
They just wrote the same thing and they said something inappropriate about the gentleman who's standing and something sticking out.
so back there, we were told this is a stick figure who has a hurt toe, like it's a swollen toe.
Hurt toe.
See, that's
That's a toe.
that's a toe. So we're going to form this intermediate. How are we going to resolve the intermediate? What's going to be the next step?
Protonate the oxygen.
Protonate the oxygen. Why not? Why don't I just kick off one of the arms?
It's
Methyls
never
fly
kicked
away
off.
by themselves.
Yeah, methyl's not going to be a leaving group. Absolutely. That's bad. Ugh. So notice that what happened here is we had two carbonyls. At the end of the day, one of them is still a carbonyl. The other has become an alcohol. This is a process called carbonyl condensation, where again, we imagine when we have a carbon, an alpha carbon, that is a carbon next to our carbonyl, we have the opportunity for a base to deprotonate it and form that carbanion, because in reality it's in some kind of resonance state that makes that all possible, that makes that not as terrible as we would otherwise imagine. And then when we attack, we form our carbanion and we attack. If we attack, there we go, our carbonyl and we don't have a good leaving group, we just protonate. And that is technically called an aldol condensation. You may have encountered them in OChem too, but if you didn't, here, aldol condensation. Yay, we form our carbanion, we attack something that doesn't have a leaving group, so we're forced to protonate. But we could have had more fun. What if we had something that does have a leaving group? And this is pretty easy. If we go back to our original drawing and have, I don't know, some kind of isopropyl ether kind of thing going on. If we had a little ether linkage at the end of this guy, our intermediate state would have had some, there we go. We would have had this intermediate state. He's holding like a crab in his hand, I don't know. Wishbone, yeah, okay, he just ate a big turkey. And we could resolve this now by allowing this to collapse back down into a carbonyl and kicking this guy out as an alcohol. Make sense? If we do that, what do we get at the end? We get a final structure that has 2 carbonyls. We had 2 carbonyls come in, 2 carbonyls enter, 1 man leave. We had 2 carbonyls come in, and we end up with a structure that has 2 carbonyls. That's technically called a Claisen reaction. And again, you know how I feel about named reactions. Don't ever learn that word. It's a carbonyl condensation because what's happening? 2 carbonyls are being condensed together. That has meaning. Claisen is just some dead German guy's name. Don't waste your brain power on it. That make sense? Okay. We have one more little reaction to do real quick, and then we're going to do a group activity to really cement our knowledge of these and make you feel really embarrassed because we're all going to get up on the boards. Oh, I know. Here we go. The last type of reaction I want to mention is an elimination reaction. We've already seen now a lot of reactions that start with base deprotonates something. And this is relatively rare in biochem. You won't see a lot of these. So for instance, in glycolysis, which we're starting next week, there's 10 steps. 1 is an elimination. In carbohydrate metabolism from start to finish, there's about 32 steps. 1 is an elimination. So we're not going to see this often, but it does occur. And this is the idea where our strong base pulls a proton off a hydrogen, and on an adjacent carbon, a leaving group leaves, and we're left with a double bond. Again, we are hindered in doing this reaction in biochemistry by the fact that we don't have any good leaving groups. Leaving groups that are worth a darn are vanishingly rare. Right? So that's going to be a real limitation. The most common leaving group we're going to see is a terrible leaving group. The most common leaving group we're going to see for these kind of reactions is an OH, which doesn't even really want to leave until we protonate it and turn it into a water. So we're going to have to invoke a proton somewhere around here, right? Good old invoke.